In this lesson, we're going to study two concepts, finding the arc length and finding the area of a sector of a circle, that use radian measure. First, we'll look at the arc length concept. We'll go to our definition of finding the measure of an angle in radians. We'll start with our angle theta in standard position, and what we know is that if we want to get the measure of theta in radians, that the way we do that is to take the length of this arc, which we will call S, and we divide it by the length of the radius. Now, what if we want to find the length of this arc? Well, of course, we know for the whole circle that that would be the circumference, and we know that we can find that by multiplying 2 times pi times r. But what if we just want to know the arc length of a sector of the circle? And what we mean by sector of the circle, this right here, this would represent the sector. Well, the way we're going to do that is to solve this for S. We'll multiply both sides by r, and so we get that the arc length is equal to r times theta, where theta is what we call the central angle, and where r is the radius, and of course theta is measured in radians. So let's look at that definition. The length of the arc intercepted on a circle of radius r by a central angle of measure theta, radians, is given by the product of the radius and the radian measure of the angle, or S equals r times theta, where theta is in radians. And notice the caution. When applying the formula S equals r theta, the value of theta must be expressed in radians. Now, we'll work some problems with this formula. Our problem number 1 says find the exact length of the arc intercepted by the given central angle. Well, here's our central angle, and it measures pi over 3. That's what that's telling us. The 15 is telling us that that's what the radius is, and so they're asking us to find this distance S. The length of the arc intercepted, well, we're saying that that's one ray of the angle, that's another ray of the angle, and it intercepts this arc. So, to find S, we know that that is r times theta, where theta is in radians and pi over 3 is a radian measure. So we'll take our 15 and we'll multiply by pi over 3. Now, when I work these problems, I always like to have units for my radius. Sometimes in the book they don't give you units, but I think maybe we'll just pretend here that this radius is 15 inches. Notice it says exact, so what we'll do here is we'll say 3 divides into 15 5 times, so we'll have 5 times pi, and that would be what we consider the exact length of our arc. And since our radius was inches, then this would also represent inches. So this arc length would equal 5 pi inches. Now very often we want you to leave it like that. If you want to use your calculator and take 5 and multiply it by pi, and be sure you use your pi button on your calculator, and round, then you could give the approximate value. So the approximate value here would be between 15 and 16 inches, but this would be our exact value. For problem number 2, find the length of the arc intercepted by a central angle theta equals 30 degrees in a circle of radius 5.45 meters. Well, you could draw the whole circle, but I think I'll just draw the sector. And if you want to imagine that, the circle came on around like that, of course we know that the central angle comes from the center of the circle with two rays forming each side of that angle. And we know that this is 30 degrees. This distance would represent our radius, which is 5.45 meters, and they're asking us to find this arc length, which is S. Well, of course we know what we have to do. We multiply theta times r, but what's the problem with theta? Theta must be in radians. So here's what I do with it. Let's put our r, of course that's 5.45 meters, and then I write my theta in degrees, but we know how to convert degrees to radians. We know that we multiply by pi over 180. Now the truth is, I would expect you to know that 30 degrees is equal to pi over 6. So that's what I'm going to do with it. I'm going to write 5.45 times pi divided by 6. If you need to see it, 30 goes into 30 once, 30 goes into 180 6 times, and so that's where you get pi over 6. So on your calculator, we'll calculate this out. We don't usually find exact values unless this divides evenly into that. So we'll just calculate it. It doesn't say exact. We'll round, since this is to 3 significant digits, we'll round to 3 significant digits. Simply take your 5.45, multiply it by pi, divide it by 6. And remember to use the scientific calculator and use the pi button. And what we get is 3 significant digits, 2.85, and of course that would be meters. On our third problem, it says find the radius of a circle in which a central angle of 4 radians intercepts an arc length of 5 feet. So what they're doing here is they are giving me theta and they're giving me the arc length. So maybe I could draw that. Let's see here. I'm going to put my angle that way. 4 radians, well I know to here is about pi radians, 3.14. So I'm going to say 4's down here somewhere. This probably won't be true to scale, but it'll be close. So there's my arc length, and it tells me my arc length is 5 feet. So I know S is 5 feet. And I know that my central angle, theta, is 4 radians. So what they're really asking me to find is my radius. And once again, I use my formula. I know that S equals R times theta. And in this case, my theta is in radians, so that's not a problem. So I'll substitute my 5 in, because that S stands for my arc length. I'll write my R, and my theta is 4. So to solve for R, I'll divide both sides by 4. So R equals 5/4. And I would just leave it like that. If you want a decimal approximation, of course it's not even an approximation, it's 1.25, and R will have the same measure. Since S is feet, R will be feet, and so I'll just put feet right there. Now, those were pretty basic examples of arc length problems. Let's look at some other problems. Problem number 4 says, find the distance in kilometers between each pair of cities, assuming they lie on the same north-south line. And the pair of cities that we have here, we have Halifax, Nova Scotia at 45 degrees north, and Buenos Aires, Argentina at 34 degrees south. Now, here's what we imagine. They're telling us they're on the same north-south line. And so we take our Earth, or imagine a globe, and we take a cross-section of it so that that north-south line is represented here. And I'll go ahead and complete a cross-section of our Earth, which is a sphere, would be a circle. And we'll put the equator right here. And of course it would be all the way around. But I'm also going to label the radius of the Earth. They tell us that that's 6,400 kilometers. Now, if these two cities are on this north-south line, what this means is Halifax, Nova Scotia, 45 degrees north. It means that it is on this line so that the central angle between the equator and this line out here is 45 degrees. And of course we know north is that direction. So that means that that's where Halifax is located. And now Buenos Aires is 34 degrees south. So that means I'm going to come this direction, and that angle right there is 34 degrees. I'm going to redraw this. Not so good at my circles, huh? Okay. So this angle is 45 degrees. And down here, this angle is 34 degrees. And this is where Halifax is. And this point would be where Buenos Aires is. Now, find the distance. Well, they're asking us to find this distance, and that would be the arc length, where the 45 degrees plus the 34 degrees would be the central angle, and then of course the radius is 64 kilometers. So to find S, we'll say S equals R times theta. Well, we know our R is 6,400 kilometers. But our theta, we're going to have to add the 45 degrees to the 34 degrees, and we get 79 degrees, but we can't use it like that, can we? So what we'll do is we'll convert it to radians, because to use this formula we have to convert it to radians. And of course the way we convert it is by multiplying by pi over 180. So we'll calculate this. I'm simply going to say 6,400 times 79 times pi divided by 180, and use your pi button. And it looks like to me everything's in two significant digits. So what I get here for this arc length, or for the distance between these two cities, I get 8824.38, but rounded, and since it's rounded I'll do approximately, is 8,800, and that would be kilometers. The arc length and the radius have the same measurement. And of course, remember that since theta is in radians, that is just a number. That is not a type of measure. So it's just this number times 6,400 kilometers, and that's how we get the 8,800 kilometers. Now let's look at the next problem. It says find the radius of the pulley in the figure if a rotation of 62.3 degrees raises the weight 15.2 centimeters. Well, here's the weight, here's the pulley, and this pulley along the edge of the pulley, which would be the circumference of the circle, there's this cable, and we'll label that's the radius of the pulley, and that's what it's asking us to find, is to find that distance. Well, what happens is that a pulley turns, doesn't it? So as this pulley turns, this cable will wrap around the pulley and the weight will come up. Well, what it's telling us, it says if a rotation of 62.3 degrees raises the weight 15.2 centimeters, well, if the weight raises 15.2 centimeters, that's because this cable on this pulley has been pulled up 15.2 centimeters. Well, that 15.2 centimeters represents the arc length, and it says that it's rotating 62.3 degrees. Well, that means that the angle, the central angle for this arc length is 62.3 degrees. So this pulley is going to move in this direction, and once it's gone 62.3 degrees here, then this arc length is going to equal to 15.2 centimeters, because that cable will have pulled up 15.2 centimeters if it says it raises the weight 15.2 centimeters. So we know that S equals R times theta. We know that S in this case is 15.2. We're looking for R, and the problem is that theta is not in radians, but we will write the 62.3 and we will multiply it by pi over 180, and this will convert our theta to radians so that it's just a number. Now to solve for R, I'm going to multiply by the reciprocal of this quantity. Of course, I'll need 180 in the numerator, and in the denominator I'll need that 62.3 times pi. And of course I have to do that on this side also. So of course those divide to 1, those divide to 1, those divide to 1. So I can calculate my R by saying 180 times 15.2 divided by 62.3 pi. If you're entering this on your calculator, you might want to put parentheses around that denominator. And I need to round to 3 significant digits, and so when I do, actually on my calculator I get 13.97, but when I round it's 14.0, and of course that would be centimeters because the arc length and the radius will have the same measurements. Alright, I want us to look at one last arc length problem. And first of all, notice I have my sector of my circle, and this would represent my central angle here. And for the rays here that form this central angle, they intercept the circumference of this circle, and you can imagine that the circle keeps going like this at this point and this point. And so this distance represents my arc length, but the straight line that connects these two intersection points is called the inscribed chord. Now notice, if a central angle is very small, there is little difference in the length of this inscribed chord and the length of S, the arc length. So sometimes if we have something that is straight across right here, we want to find this distance, well, we can approximate the distance by finding the arc length. And that's what we're going to do in this next problem. So let's approximate the length of a ship if the ship subtends a 2-degree 30-minute angle horizontally when it is 3 2/10 kilometers at sea. And we're told that when a central angle intercepts an arc, the arc is said to subtend the angle. So here's my sector of the circle with my central angle right here. And here's my arc, and I'll call that S. But truly, you know, ships aren't straight, aren't curved like that. They're straight. So truly, what the ship would do would be it would run from this point to this point. And so we want to find the length of the ship, but because this angle is fairly small, we can approximate it with the arc length. Now it tells us that it is 3.2 kilometers at sea, so this point would represent the shore, and out here it is at sea, letting the radius equal 3.2 kilometers. So what we have here is that R equals 3.2. We have that theta equals 2 degrees 30 minutes, and we're going to find S. So S is R times theta, so we'll say 3.2 kilometers. And for theta, the problem is we have to change it to radians. I would go ahead and write that 30 minutes is half of 60 minutes, isn't it? So I would go ahead and write that as 2.5 degrees. You can do that in your calculator. So we'll take 2.5 degrees and we'll multiply it by pi, and we'll have an approximate value here. It looks like this is just a 2-digit, so that's what we'll round to. And to 2 significant digits, I get 0.139, so let's see, 0. Since it's 0.139, this will round to 0.14 kilometers. So our ship is approximately 1,400 kilometers long. Now we're going to look at another application of radian measure, and that's how to find the area of a sector of a circle. So let's look at that concept. Alright, here's my sector of the circle, which you can think of a sector of a circle as part of a circle. Here's my central angle. Of course, that means the angle is at the center of the circle. this distance represents the radius of the circle. And of course, when we talk about the sector, this is the sector. We talk about the area. That, of course, is we want to know the measure of that shaded part. Now, we will derive that formula, and to derive that formula, we use our knowledge about the area of a whole circle. And so, if we wanted to find the area of this whole circle, it would equal pi r squared. Well, as it turns out, there is a proportionality between the central angle and the area of the circle, or the area of the sector. And that's what we're going to use. I know that the area of this whole circle is pi r squared, and it is to the central angle of this whole circle. And what is the central angle of a whole circle? And we want it in radians because, of course, we've already got our pi radians. This central angle for the whole circle is 2 pi. So the area of the whole circle is to the central angle of the whole circle as the area of the sector, and we're letting A represent the area of the sector, is to its central angle, which would be theta. And once again, theta must be in radians so that it is just a number. So let's take this and we will solve this proportion for A. So let me see here. I have pi r squared is to 2 pi as A is to theta, where r represents the radius of the circle, where A represents the area of the sector, and where theta represents the central angle for the sector. So let's take that and we'll solve it for A. The first thing that I'm going to do is those pi's divide to 1, and then I'm going to cross multiply. Since it's a proportion, I know that 2 times A equals r squared times theta. And then I'll divide both sides by 2, or I can multiply both sides by 1/2. I think I'll do that. So the area of the sector of a circle is equal to 1/2 times the radius times theta, where theta is the central angle for that sector of the circle. We have a problem to work, but you might want to write that down. That's exactly what I just said. The area of a sector of a circle of radius r and central angle theta is given by A equals 1/2 times r squared times theta, with theta in radians. And caution, as in the formula for arc length, the measure of theta must be in radians when using this formula for the area of a sector. So let's work this problem 7. It says find the area of a sector of a circle with r equals 64 5/10 kilometers and theta is 4 pi over 3. Let's sketch that. I know all the way around is pi radians. 4 pi over 3 is down like this. So I'm just going to, but the center of my circle's a little off, isn't it? You might want to use your imagination here. This central angle is 4 pi over 3. That's what they're telling us. And this radius is 64.5 kilometers. So when we find the area, we'll say 1/2 times r squared times theta. Our r is 64.5, and we'll square it, and since it's kilometers when it's squared, that's how we'll get our area unit of measurement of squared kilometers. And then theta is in radians, so I don't have to worry about converting it. And you know, if you need to, you can put that over 1, so you're looking at the numerators of your fraction. I usually go ahead and say 64.5 squared times 4 times pi, and then I would divide it by, you can do this in your head, can't you? 2 times 3 is 6. So square this, multiply by 4, multiply by pi, and then divide by 6. And we'll round it so it'll be an approximation to 3 significant digits. And I get 8,713. If I just need 3 significant digits, that would be 8,710. And once again, that's area, that's kilometers square, and you get it when you square that 64.5, that's kilometers. For problem number 8, we're also finding the area of a sector. We're given the radius, and we're given theta is 172 degrees. So that would almost be to 180. So let's see here. Pretty flat circle, huh? And we know that the angle, this angle, is 172 degrees. We know the radius is 21.2 kilometers. So we'll just use our formula. But this time, we'll convert theta. That would be 172. We'll multiply by pi over 180. And once again, I would just calculate this. The 2 and the 180 are in the denominator, and usually I just would say 21.2 squared. I'd multiply that times 172. I'd multiply that times pi, and then I would divide by, and what you've got to divide by is 2 times 180. So one way to do it would be push divided, parentheses, 2 times 180, close parentheses, and push your equals, or your enter, depending on what type calculator you're using. And let's calculate that, and let's round that. And we want 3 significant digits according to what's given. So that would be, I get 674.6. So it's going to round to 675. And once again, that would be kilometers squared, or squared kilometers. All right, let's look at 2 more problems that we need to use this area formula for, but we won't be finding area. In one of them, we'll find theta, and in the other problem, we'll find the radius. So let's look at problem number 9. It says, find the measure in radians of the central angle of the sector with r equal 5 and the area of the sector equal to 20 square units. And so here I've got a circle, and the radius is measured, it's 5, and it doesn't say what units, and since it just says units here, it would just simply be, we'll call it 5 units. And here's your sector. Now I've got the sector shaded, and we're looking for theta, and we know that the area of the sector is 20 square units. So we'll use our formula. In place of A, since our area is 20, we'll write the 20. In place of R, we'll write 5 squared. And then we're looking for theta. So I'm going to square the 5 first. And then I'm going to go ahead and say 1/2 times 25 is 25 halves. And then I need to undo multiplying 25 halves times theta. I'll multiply both sides by 2 over 25. Of course, those divide to 1. And so theta is equal to 2 over 25 times 20. Let's reduce. 5 goes into 20 4 times, and 5 goes into 25 5 times. And I get 2 times 4, and in the denominator I get a 5. So theta is 8/5. 8/5 what? It is 8/5 radians. When you use this formula and you are given the radius and the area, when you solve for theta, it will be in radians. You may leave it like that. You may write the decimal equivalent, which is 1.6. That's up to you. It doesn't say that we have to do it exact, but either one of those would be good answers. For this last problem, we're to find the radius of a circle in which a central angle of pi over 3 radians determines a sector of area 81 square feet. Okay, well I think I'll sketch it, and pi over 3, that may be too big. This angle I know is pi over 3, and I'm looking for the radius, which would be this distance, and I know that the area is 81 square feet. So we'll write our formula. Our A is 81. We are looking for R. Our theta is in radians. It's pi over 3. So what I need to do is to solve this equation first for R squared, and then I'll solve it for R. I need to undo this multiplying by pi and dividing by 2 times 3 is 6. And maybe some of you need to see it like this. We can say 1/2 times pi over 3. 1 times pi is pi, and 2 times 3 is 6. And now, to undo multiplying R squared by this fraction pi over 6, I can multiply by its reciprocal. Those divide out, and I get that R squared equals 6 times 81 over pi. So if we extract roots, R equals the square root of 6 times 81 over pi. And I'm just going to calculate that value. Remember, when you extract roots, you really get R equals plus or minus, but since R refers to the radius of a circle, that it can't be negative, so we only have to worry about R equals square root of 6 times 81 over pi. And I got, let's see, we only have 2 significant digits. I got 12.43, so it'll just be 12. 12, what will it be? Well, if the area is in square feet, the R will be feet. And what I did, I used a scientific calculator. I said 6 times 81 divided by pi, and then I pushed my equals to get it to divide, and then I took the square root of it. This completes the lesson on applications of radian measure. If you're finished with the tape, please rewind it before you return it. Thank you.